All right, it's Friday afternoon. Spent a long day doing a whole bunch of measurements after a long day of frustration yesterday, realizing that the measurements I made early in the week were being misinterpreted by me. And so I'm going to make this video to explain what actually happened and what's actually going on with the system. A lot of progress. I have the frequency synthesizer installed, and that's this guy over there. And I was originally going to use one which had I needed the socket, and the socket proved to be kind of a disaster. The ground for the chip I was going to use is on the bottom. It's a pad. The socket does not pin out the ground, so I had to take apart the socket, solder on a ground wire, and I installed it. And I needed to use that because this the circuit, or this chip, um, it's it's a frequency synthesizer, and normally there's a crystal, but this one has a clock in, and it's only available in that nasty package. And I had previously tried to use this version, which is a $5 board from Amazon, and it has a version which has a crystal on it, and and it's supposed to be 25 megahertz. And I looked in the app note, and I saw a reference to the fact that you could drive the crystal input with 1 volt peak to peak through a coupling cap. And so I tried that after I had bought this $100 socket, and it didn't work. And I kind of gave up. When I got the socket, there was excessive noise on the chip, and it wasn't working right. And I thought it was the board, noise on the board. It wasn't that. So I decided to try this clocking circuit again, and it still didn't work. But then I discovered that the DAC and this frequency synthesizer share an I2C address. It's the same I2C address. So actually, every time I wrote to the DAC, I was clobbering the value that was in the frequency synthesizer. So naturally, it wasn't working. Put that in there. Lo and behold, it works. Very, very happy. Let me explain what this chip does. Basically, there are two PLLs. That's the first stage, and so it multiplies whatever clock you have coming in, and then it has multiple output stages which then divide down that clock. And so the PLL wants to be at a nominal 900 megahertz. Then you can divide it down, and that's what's happening here. I have 10. I'll show you on the circuit diagram. I have my 10 megahertz coming in. It goes through it's 5 volts. Goes through a voltage divider, and it goes through a coupling cap into the synthesizer. And the synthesizer has 3 outputs. They're either on these SMA style, or there are these pins, and that's the voltage divider and the coupling. And so when it comes in, it gets multiplied, and it gets multiplied by an amount which is part integer and part fraction, and the integer part is from 15 to 90. So for the 10 megahertz clock, it goes up to the 900 megahertz maximum. And there's also a fractional part, which is 20 bits, and so it can be any fraction with 20 bits over 20 bits, so a million basically. And then it goes through a divider stage, which has a integer divider and again a 20-bit fraction, and there the divider can be 8 to 2000, and then there's a 20-bit fractional part. And because of noise issues or jitter issues, you want to keep the integer, you want to keep the divider part integer, because to make the fractional part work, it'll make one of the edges a little bit sooner ever so often. So that adds jitter. So if you can't shrink all the edges, it'll shrink some of the edges, and that gets a big jitter peak. So you want to actually do most of your dividing in the multiplication stage, And so then if there's a little bit of jitter there, that jitter is reduced by the factor of your divisor. So my goal was to have it be able to set a frequency down with a resolution of a hertz. So the algorithm I use is I figure out the divider first by take the lower decade of 900 megahertz, which is the max, divided by the frequency I want, and then the PLL stage will therefore be that divisor times the frequency out. And I take a decade of that, so then it's always a power of 10. So then when I do my multiplier, I have enough bits to do that, which I'll explain. And then the multiplier is just the PLL frequency divided by my reference, which is 10 megahertz. So for example, if I want to do 14.074238, I take the 900 megahertz divided by the frequency, and I get 63 point a bunch of stuff. That's way more than 20 bits of fraction. So my divisor is 60. I then multiply 60 by my frequency, and I get 844 and some stuff megahertz. I divide that by 10 million and get my multiplier as being 84 for the integer part, and then the fractional part is 445,428 over 1 million, which these are both 20-bit numbers. And so I will not have an error in my final value. And so that's how and then you program this into the chip, and then the magic happens. So that's how the programming works. So let me get rid of the board. What's this all about? Well, the goal here is to do what's called a frequency measurement test. And it's a contest, and they send out a reference tone at some frequency, and you kind of know the range, and you're supposed to actually measure it. And so you get a green box if you're within a hertz, and the reporting is to 10 millihertz. My goal is to be, better than 10 millihertz with my relative frequency method. And of course, I cross this out because there's some errors here. And so I thought I was testing this against WWV, which is a reference at 10 megahertz. And the way I did this, which will be the way you do it in the actual contest, is I put a reference tone at just under that, 400 hertz under that, and I set my radio to 600 hertz below where the WWV signal was. It turns out I was measuring my own 10 megahertz signal, which is leaking off of the oscillator, and I thought I was getting WWV because I could hear the voice and the tick-tocks of WWV, but those are actually on side bands that aren't part of the 10 megahertz. So my 10 megahertz was clobbering, the 10 megahertz of WWV, even though I was hearing the tones or the voice on it. So what happens is I tune my radio, and this is supposed to be radio accuracy invariant. So I tune my radio to 999,400 supposedly, and my tone sits here at 999,600 and 061. There's this fractional part because I hadn't worked out my algorithm, so I do have an error in there, but I know what it is. And then WWV, which it isn't, is about 400 hertz above that. And I use a program called FLDigi, and it shows up as audio after it's been demodulated. So basically you subtract out the radio frequency. And when that happens, since I subtract the radio frequency, in audio, I'm tuned relative to 0 hertz. And my tone from my oscillator showed up at 212.7243 hertz. So it was 212 hertz above, but it was supposed to be 200, which means my radio has an error of minus 12.7090 hertz, and the WWV not station was at 612. And so when I do this in real life for the test, I want to put my tone really close to this, and I measure that difference. And then when I do that, I can then calculate what that unknown station is. And it doesn't matter, the radio can be moving back and forth, or I'm off by 12 hertz here. It doesn't matter because I'm actually measuring the difference between these two frequencies, not their absolute value. And I'll show that the radio actual tuning does jump around. So, okay, so where am I here? So the radio error was minus 12 hertz, which is kind of what I actually expect, because there's a calibrate function that I did on the radio, and it came up with 1.3 ppm was the error in the radio, or what he had to add to it. And so the radio knows that. Of course, I cleared that out, but that's what the error is. So then when I measured the tone relative to WWV, which is actually my 10 megahertz relative to the frequency I'm producing from that 10 megahertz, I got that I was off by 0.0007 hertz. And when I averaged that over 75 samples, I was basically 570 microhertz away from the actual value. So I wasn't measuring WWV, but that's the accuracy of the measurement technique of the oscillator with something that's produced by the oscillator. So that is how accurate the whole measurement setup is, because the tone in my 10 megahertz were exactly 399, 984 hertz apart, and basically I measured that within whatever it says here, 57 parts per trillion. So so fundamentally this is a very accurate measurement. It turns out that the thing you're actually measuring when it comes over the air, that varies by a lot, and so my measuring tool is far more accurate than the natural variation of the signal coming in, which I'll discuss. One of the things I was worried about, the PC, the PC is actually measuring this tone, and it doesn't necessarily have a perfect clock either, but it's synced to GPS, and so the audio measurement, has a high but unknown precision. And so what I wanted to do to figure out this is imagine that I'm trying to measure, a 200 hertz and a 600 hertz tone, and if my PC introduces a 0.5% error, the 200 hertz will be 199, the 600 will be 597, and so you get 398, and you don't know if that's what the actual measurement is or it's because of the error. So I was going to do an experiment where I actually measured multiple spacings, and if you measure multiple spacings, my reference to my reference at 600 more hertz, I know precisely that's 600 hertz. So if I measure it on the PC and it's something else, I can calculate a scale factor. So I was going to do that. So that's actually what I did. So I'll show you some measurements, and the radio has both its own internal oscillator, which is this TCXO, temperature compensated crystal oscillator. And what I did is, this is showing the measurements of the raw tone and the reference tone. And so this is all, again, coming from me. And this is a plot over time, and this is a couple minutes of the data. You see that it jumps around by about 0.05 hertz, and it's bouncing around a lot. And so you think, that's no good. How are you going to get your 0.01 hertz accuracy? Well, what really matters is the difference between these two values, not its jumping around. And so when I look at that, actually, let me show you. I switched to the GPS, and the GPS is a thing that I put into the clock, And again, the GPS, when I did these same measurements, again, my tone compared to the reference tone. Actually, the reference tone actually was the GPS I was feeding into the radio. So the radio is actually measuring its own 10 megahertz, not the 10 megahertz that's sitting on my board junking things up. And what you see, very, very curious, that there's almost, you can see the periodicity of these frequency jumps. And this is probably the filtering algorithm inside the device, messing things up. So so that's something that's I have to worry about. And then there are these big deviations, and I'm not sure what causes this. This might be something on the PC, but it's relatively stable. And then boom, something happened here, and I think that that's actually a PC measurement artifact, which I need to be cognizant of. But anyway, good results. And if I look at the delta, here's the delta between 200 and 300 hertz. You see that it's very, very small. Most of the time, it's within point. I mean, this is easily 0.0005, like I thought, like I was measuring. But sometimes it has these big jumps, and these almost look like they're quantized. This looks like twice as much as that. That looks like half of that. I'm not sure what's going on. But I did a bunch of work, and the frequency that you use, these frequencies are so close, they interfere with each other, and they cause jitter, and they cause noise on the board, which causes the frequency to change. So there's lots of coupling going on. And so actually when I do the real frequency measurement test, I'm not going to have the 10 megahertz beating on the 10 point, blah, 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 100 hertz away. So it'll be cleaner, but I do have to be aware of this. I then moved to a spread of 700 hertz, and here I actually cleaned up the board. I cleaned up some of the traces on the board, and you can see it's very, very clean. And actually, if you go into the data and look at it, it's that 0.0005. So 500 microhertz is the delta. But again, these fixed errors, they're very, very constant. Very, very curious. And again, I'm not sure what it is that's causing that. So I need to debug that. But and you can see the width of these is, and they're all the same width. So if it was random noise, it wouldn't be this regular. And I don't know if it's, Chrome refreshing, or I got some mail that came in, but there are these periods where it does vary. But the rest of the time, again, very, very accurate. So I have, again, my tool has the accuracy to measure to the level that I need. So the next step for me is to measure actual signals, WWV for real, and I have to find a signal that I'm not going to be measuring my own signal. And I did some experimentation, and the atmosphere moves around. These signals get reflected off the ionosphere, and so that layer moves around. And actually, you can detect, you get a Doppler effect from that. You can detect that, and so sometimes the Doppler effect can be as much as 0.1 hertz, which will kill your accuracy. And the way you have to maybe filter that out is to measure a reference signal nearby where this test tone is coming from, so you can figure out how the ionosphere is moving, so you know what the frequency shift is. And it varies over minutes, and then you can take that into account as well. So my real accuracy is going to be stymied by propagation, multipath, and this ionosphere moving effects. So that's going to be fun to investigate. And then I need to debug what's going on here, or at least be aware of it. And you can tell when your frequency boom, jumps for a while and then goes back to its nominal value. The problem is frequency measurement test is like a minute, and so this lasted for about a minute. So if you're doing it here, your value is going to be all wrong. Anyway, I'm glad I made a lot of progress, figured some things out. Still don't know. So I know how accurate my system is. I just don't know how accurately I can measure a test signal. Anyway, that's the progress, and hopefully we'll have some actual frequency measurement test things I can present next time. Thanks for watching.